Very scary. Platinum, very scary. Okay. I guess, yeah, just do it. Right, okay. Okay, I'll just do the same thing, start at 05. Okay, let's see, what are my goals for this? Because I'm not going to do well, just because it's plat and I haven't practiced plat at all. If I can get, I think the goal I set last night was first two subtasks, or the first subtask of 2 problems at least. Oh, how nice. These problems are like, okay, this one's not the same. This problem is kind of the same. Okay, read. Oh wait, print them. Print things. Jeez, this looks annoying. No. This is mean. Okay, so it's 1.1. Okay, 1.1 actually works out pretty well. 3 pages. Okay, let's do this. All right. Okay, read. Have a line again. 3 cows. At least 3 cows. 3 cows and 2 almost cows. So it's like the gold problem, except now you choose a 3rd cow. This is scary. Okay, let's see. N equals, I can do n is 50, right? It's literally just, you go through every, you can literally just, right, just go through every triplet and check. Alright, so I could probably get 5. So I'm thinking N 100 nodes, a single receiver or neither. Single as people number of receivers. It's less than K, so we always go to the larger one. Aside from K, 0, 1 or 2, no subgroups. An endpoint. Huh? Okay. What is the pass? Okay. Oh, I thought we just said they don't share. What? What is V? I am confused. Isn't that like a Euler tour or something? Or an Euler tour, except directed. Okay. Ooh, quite a couple samples. Alright, this looks scary. Probably. Why is all like tiny n? Tiny n usually means cancer. Same log coordinate. Okay, so this is probably another one. This is probably similar to the gold P3, where we have a Kansas DP after you make a bunch of clever observations about shapes. Okay, let's see. So if I remember correctly, in gold, I should remember correctly. It was literally yesterday. Problem 2 was hard to understand but easy to actually solve. So maybe I'll start with that because I don't actually fully understand what the heck's happening here. E. What is E? What is E? I'm confused. Where is E? Okay, that was not helpful. I don't? I'm confused. Okay. Ooh. Yeah, okay. Okay, wait. Restart. Wait, let me open the windows. Kind of warming here. Okay. Cool. Okay, we have, network of n nodes. Okay, cool. Okay. A sender, receiver, or neither. The number of senders is equal to the number of receivers. The connections between the nodes in this network can be described as a list of edges, each of the form I to j, meaning that node I may route to node j. Okay, normal enough. Interestingly, all these edges satisfy the property that I is less than j, aside from k, which that satisfy I is greater than j. Okay, and k is very small. There are no self-loops, which are edges of the form I to I. Okay, cool. So we have directed network, which almost forms a DAG, except for maybe one or two edges which don't form the DAG, which make the DAG not a DAG. Okay. The description of a routing scheme consists of a set of S-directed paths from senders to receivers, such that no two of these paths share an endpoint. What? The description of a routing scheme contains and consists of a set of S-directed paths. Senders? Multiple senders? Or a sender? I'm going to assume a sender to a receiver, such that no two of these paths share an endpoint. Yeah, I don't get that. What does that mean? They don't share an endpoint? Why would they not? How do they what? Are you saying that, like, the paths don't visit the same node multiple times? Oh, no. So scheme is a bunch of paths, and then it defines a path. Okay, that makes more sense. That is as the paths connect distinct standards just like the okay. Isn't this like flows, except I don't know how to do flows? How to know sender S to receive armor can describe the sender to nodes S blah 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 blah. Node may appear more than once within the same path. Okay. How to number the scheme routing schemes such that every directed edge is traversed exactly once and something answer may be very large reported module 10 to 9 plus 7 is guaranteed that all at least one routing scheme satisfies it. Okay. This input contains T. Note that S is not explicitly given within the input. Okay, I see how it's sender, receiver, and neither. Move arms in the string, we could also use at least one S. Yes, and lines of each test business system. The string M0s and 1s of J's bit of the I find is equal to 1 if there's yeah. Okay. Blah. Okay. N is less than or equal to 6. Okay, let's see. How we unfactorial this? I think what it could, okay, so what you could probably do is you could do like a double recursive, where you generate all the permutations, and then for each permutation, you split it into paths if possible. Wait, but you can come back, you can visit nodes more than once, right? So that might not work. Yeah, no, maybe appear more than once within the same path. Okay. And it's literally less than equal to 6. Wow. This is duh. I mean, I don't even know how to prove this. Wait, okay, so a routing scheme needs to contain what? Every directed edge is traverses. Wait, okay, so we can just order. Oh no, we have n squared edges, don't we? Right? Yeah, because well, not n squared over 2 plus 2 or something like. Okay, whatever. We have a not small. Well, actually, no, we have like 2 to the. We have 18-ish, 20-ish. Bit massive DP, but on a brute. Okay. First, should taking a nap before this contest. It's been like not even 20 minutes, and my head is already spinning. Yeah, I just don't know. Maybe because there should be a way to just generate all the routing schemes. Wait, how many? We can't actually have. Wait. Okay, wait, let's just assume for now k is 0. K is 0. We have a DAG. So what if we permute all the senders and receivers? Put the first sender, or put the sender, and no, it has to have permute all the senders, permute all the receivers, match first sender with first receiver, second sender, second receiver, and so on. And then within each of those permutations, we recursively go through, right, it's not that, it's 3 factorial times 3 factorial, which is 36. There's 36 different configurations of those at most. And then for each of those, we go through and we find every single path from one receiver to the other receiver. And then we do that for all 3 pairs. So how many different paths can there be? I think it could be 6 factorial paths, right? Because we can go, or no, not 6, just, no, 4 factorial, because we could go to the 4, well, not really 4 factorial, but let's just say 4 factorial, right? So then that's what? 4 factorial is 24. So 24 to the 3rd power, right? Because you have to try all of them on all the different things. So 3 factorial times 3 factorial times 4 factorial, which is 6 to the 3, which is 6 to the 3 times 4. 6 to the 3 is, I'm bad at math, 6 to the 3, 36 times 3 is 216 times 4 is small. It's like 800. It's 868? 864. Yeah, 864. No, but you can go through multiple times, right? So it's not actually 4 factorial. Okay, so given a graph, how many different paths from node S to node E are there? And then just find all of them. Right, so that would get us, assuming this actually works, that gets first subtask. And then maybe we can solve k as 0 as well. Okay, let's see. So there's third one. Wait, can't we do the same thing I did for the gold problem where you count the number, except now it's times the number, it's minus, so then we also keep track of the number of, like, any duplicate. Like, so you have one duplicate count, which is the number of duplicates, so that there is a possible, it's like number of duplicates. How do I explain this, right? So we do the same thing we did earlier, right? So we do fix the left, find the last possible point on the right, and then you can do what we did earlier with that seg tree, right? Because now the answer would be, actually this may not work. So maybe I'll put this thing outside. We count the number of duplicates. We need to make sure the third one's inside the range. Let's see. At least 3 cows. Turning backwards. So okay, so why wouldn't just extending my full solution work? So we can't just also count the number of numbers such that there's only one occurrence of them in the range, because then we might end up extending the range accidentally. So like our right endpoint ends up being closer in than our middle endpoint, right? And then those values might not be valid, or they might be valid. We don't know. Oh, okay, how does this go for an n squared, right? How do we get n squared? So for an n squared, we can fix left, we can fix right. Yeah, actually, n squared should be pretty easy, right? We fix left, fix right. And then for the third, we just count how many values have exactly one occurrence, right? And that can be done easily by just keeping like a count, right? And just updating the count. Yeah, okay, so n squared I think is trivial. Maybe we could say we have a seg tree. But actually, we can do some seg trees, can't we? So we could say this value here stores the number of unique values. Okay, but we also would need to check if the value, if that value has a duplicate or not, right? So how would we check that? Okay, let's just say we can. Okay, so what do we want? We could say we fix the left endpoint on the right endpoint, and then we find the biggest possible interval, and then we take the sum inside that interval, where the sum is the number of completely unique values, a number of values which will show up exactly once inside the array. And then we sum those all up across all of the different arrays. And then that's our answer. Alright, so we go. So we would need to somehow. Mostly we need to invalidate some spots. So, well, actually, no, we wouldn't need to invalidate. We would just need to validate them. So we need to add those in. Well, so we can do kind of the same idea there for gold. Some people yelling outside. How nice. Right, so we keep a seg tree, except now it's a lazy sum seg tree. And then we would store the number of values that show up exactly once in some prefix, right? And then we sum all of those. Except we would only sum them if, let's see, I'm not sure exactly what. Except minus, except we don't want to include the endpoint values, right? And we don't want to include the start point values, because then we're selecting the same leader twice. And that's sad and bad. Right, okay, so let's do that. And then
After that. Oh yes, how do we update the seg tree? So it's number of consecutive, exactly. Right, I think we can still copy kind of like the same general logic, right? So once we remove, okay, so we wouldn't be removing the next value over.
So then that would be like, if we remove a 1 and it was the only 1, then we just subtract from the entire thing. Otherwise, if there's 2, if there were 2 of them, then we add to the prefix part of the section. Because now, wait, no. We subtract from the prefix part of the seg tree because now that part's not there anymore, and then we add to the next part of the seg tree. Right. Does this work? I feel like Plat. This is basically just a DS bash, though. I feel like Plat should not be this easy. Should be some right. Yeah, I forgot. How do we check if that endpoint, that part of those endpoints that we're summing, if they're actually valid or not? So it's valid if that doesn't show up anywhere else in the prefix. Right, so we'll just start off marking everything as invalid, and then we'll mark the first, right, so we'll just have a separate invalid / valid flag. Right, and then that can be changed in update as well. Right, and will that break lazy seg? That might break lazy seg. Yeah, I think that breaks lazy seg. No, we can just keep a total count of how many of them are valid, and then that doesn't break lazy seg, right? Because then, I guess, so then we would do the point update. Yeah, that would work, and then we count how many of them are valid, and then that would work as well. I think. Yeah, that should work, right? Because you use multiply by the number that are valid, and that's how you add in. Okay, and then we keep. Right, and then, okay, so then it's just, once you remove an occurrence of something, then the second occurrence is now valid, right? And then you just keep pushing on and on. Okay, so this is just going to take some time to implement, but it shouldn't be, if this actually works, I'll be kind of surprised, but that'd be pretty epic. Okay. Seg tree. I feel like, I'm probably not allowed to copy the old seg tree, right? That would be sketchy. Okay, let's see. We want a low, oops, type of that. Low, high. We want we want a sum. We want a count. And we want a lazy. Okay, so the lazy only needs to happen on the sum ranges, right? Because on the count, we're doing point updates only, so that should be fine. Okay, st times 4 void build okay, and then
We got sum. Okay, what do we want our sum to be? Right, so we need to calculate the original prefix. So if I is less than n, then we could just this is just 0. Be clear if I do. Right, it would need to be the first one to count. Okay, it should be enough. Sum 16. Okay, build function done. You need now an update. So you need an increment or decrement or prefix or suffix. So let's just write an update. Okay, right. Sorry, I'm kind of tired. I should have taken a nap. I already said this. Okay. See, just to be sure. Right, and that should be right. Right, we only need, no, we don't need update count because it's not changed. Should we update? Okay. Right, I should probably write prop. So why is this? So how we? So I'm gonna add lazy, obviously. Maybe just with an extra factor, whatever. Okay, might as well finish with the section code at least. This is wrong. This is supposed to be lazy. This is a freaking war right here. Wait, one sec. I have the window open and I'm like in it's like short sleeve t-shirt and I'm sweating to death. Let's see, what can I do? There's like not much I can do though. Just okay, I'm gonna open the other window, which is like directly behind my computer. Oop, I think I locked it. Wait. Fun. Okay, so now I should get a breeze like blowing directly into my face, probably. So that'll be nice. Okay. Huh, that didn't really help much, but whatever. Okay, let's see. We have an update.
Okay, now I can hear people yelling, so this isn't really much better, but whatever. And yeah, I know I don't actually need to do a range because it's literally just like 1 point, but I'm doing it anyways. Okay, so we're only ever going to set things to true, so we can actually keep going. We actually don't even need to propagate. Do we? Do we need to propagate? Yes, we need to propagate because we're actually changing the sum as well. Actually, no, we're not changing the sum. It's just that when we query the sum, we just get the ones that have count as 1. But we still need to update the sum. That's not how it works. Not node. I think people are playing basketball outside. Wait, so sum should store the sum regardless. Wait. Okay, so sum should store the sum regardless of whether it's a valid choice or not. Okay, so we should create a separate. There's probably a way to do it without having to create a separate attribute, but I don't know it, so let's just create a separate attribute. Okay, so so val is sum. Yeah, sum is that. Wait, do we even need a count? I don't think we need count, do we? Yeah, we don't need a count. Count can die. Oops. That's a such thing we change for the role. Yeah, actually, let's bring that out. It's useful. Let's change this to save val instead. Ignore that. Okay. So wait, which one is okay? I need to write this down. Which one is val? And which one is sum? Sum is regardless of. Okay. So what does that mean here? Okay, these are both fine. Right here. Okay, so this means. Wait, oh, so we can't update the lazy values if we don't have a count, I think, is the problem. So that we don't know how many to multiply by. Yeah, so I think we do need a count. Okay, come.
Count comes back. Wait, let me just start bring back count. Paste that back in. Right, so sum. I am confusing myself right now. Wait, okay, so what? Why do we need all three of these? Okay, so val is the one that we want. This val is the val we're going to use, so we definitely need that. And then val. So sum is really only there so that once something becomes valid, it actually does things. Right, so sum is only needed at the lowest level. So then, because when we set something to be valid, this Pn should be capital P, capital N. So when we set something to be valid, we know what value it should have. And then count is so that we can lazily update val. Okay. Sure. Okay. And then, yeah, let's update sum as well. Right. And then there's nope, no plus. Okay, wait, these are the same value, but whatever. It's just a bit better. Okay, let me add the lazies. Right, okay. Now, so now we have an update sum and update count, right? And that still works. So update sum, we just update this sum. And okay, so should we actually be update? No, should this be update? Yeah, this one needs update val. Okay, okay, so this val should be val. Maybe, probably, these are not really. Okay. Okay, come on. Alright, alright, that's good. Okay, update count. Propagate and update. So we don't actually need to update our sums. Our sums did not change at all. Just need to update our values. Okay. Okay, so now we need void query val. This is not be a void. This should be a long. Okay, return. This does not actually need to be. Yeah, I'm gonna give up on like the if lazy blah blah blah. Let's just prop it. Whatever. I'm lazy. Kind of funny joke. Okay, that was not intended. Let's see. So we want to sum them. Please that. Okay. Sunk. Oh my god.
You do spoonerism, but while typing. Okay. Man, I need to find so many things. Right. Oops. Okay. Right, okay, so now we need to build the seg. Okay, wait, no, so we need to get our prefix, right? I didn't even define. So prefix is just how many values, how many unique values of exactly, how many values show up exactly once is the answer. Alright, let's zero initialize, that's fine. If you want to move it, okay. We're putting these in all separate. No, come on, let's put these on the same loop. What's going on? Okay. CT. So, if CT9 equals 1. Actually, no. Okay, so if it's not 1, then we have to go down. So then we also need to get now we want, okay, so we fixed our left point. All right, we're going to go through, and we can use the same trick as we did in gold, where we okay, so we do int next is lower bound. This is annoying. Okay, more macros, more macros. Plus eyes, and we actually want the next one, so it should be upward bound. And then we can be pretty sure that so each of them should have an end, so you can just dereference it directly. And then now, okay, so you have the next index.
So we want the sum of everything before the next index.
So theoretically, this should just be answer plus equals 31. Node 1 is our root. So we do I plus 1 next, and then that's already exclusive. Okay, yeah. So theoretically, that should just be it. And then we need to update things. So we would want to update. Oh wait, so we didn't do. Oh no, that was defined by the site tree building. That's fine. Okay. So we would do update count. Okay, so if next isn't n, then we update the count, and then update value at next. And then we update the value. So what's the word update? Okay, so we're updating. So now everything before the next has lost one. So from I to this one to next, we lose one, and then we also update the value from next to n, we gain one. Let's do plus one. It's fancy and it looks nice. And then we just put that. If this works, I'll be amazed. It doesn't work. Okay. No. return 0. Great. Watch us print like 1,000. 59. Yeah, that's not good. Okay, let's see. Okay, it's just the same thing we did last time. 60. Okay, so it's just way off. Okay, 16. How are we getting 16? How are we getting 16? Pretty bad. Alright, and val starts off as sum times CT. CT is either 0 or it's 1. That should not be a problem. It's, wait, prefix? Okay, wait. Okay, so next here is n. Well, actually, I could print this just to make sure I'm not like doing something stupid. Right, x is n. Yes, okay. So I'm just trying all of them. Right? Okay, so it's summing the entire range. Except some of these, most of these should be invalid. Shouldn't these be -2? We have the number of unique values in the range, but we don't want, right, minus the current value. Right, yeah, I don't think I did this formulation right. We want, right, because like this 2 can't be an endpoint. So it should just say 0. Or I think, wait, no, I think you're supposed to, wait, we want, okay, we actually want to do the update first. And that way we don't, because we don't want to count the 1 as a, the 1 should not count as a unique value because it's already included. Still way off though. Okay, so it's 2 here. So 2, I think minus an extra sum, or minus an extra count, right? Okay, so that 1 should be a 0. 6 of them. What's up with that? So 1, 2, 3, that should not be 2, because there's only one option. Because now it's counting, because it thinks it can choose itself as a leader again. So, let's see. So we just want to subtract. Okay, we just had a quick hack. 1, 2, 1, 2, 4, 1, 2, 4. Okay, now we just need to get rid of, what is this 5 doing here? The 5. How are we getting 5? Wait, actually, why doesn't that work? Right, we could have, well, I mean, we only have one of them, but. Oh, it is there, it is there. It's not. Okay. Good. Okay, so that's just 5. This is 5. It should be going down as we go along. Yeah, okay, that's not good. What's going on here? Oh, I'm bad. Okay, also let's put this outside, just because it's a... okay. 11. Still not right. So you can't... Oh, yeah, so you get 1. Okay, wait, I've forgotten what these triplets of numbers are. Okay, let's merge these into a line. Okay, this is... this. 5, okay, lines up. Still 5, okay, lines up. 10. Should be 9, and they should just stop. Wait, what? These literally, these do not add up. We jumped 5 from here, but here we're adding 3? I mean, this isn't right either, but it's, oh no, actually no, this is right. 2, 1, 2, 3. Oh, okay, so somewhere I'm probably not propagating. Maybe I'm propagating bad. I am propagating though. That's weird. There's supposed to be 1 and not true to make a difference, but. Right, and the CTs should all be. Oh wait, did I not? I didn't update. Oh my god. Okay, that would explain it. Okay, let's try that again. That's not 9. Okay, so we will get positive points. Positive points always good. Well, that's sad. That's very sad. Let's see. Let us see. Okay, if we just try a simple, like just 1, 2, 3, 4, 5, 10. Is 10 correct? 1, 2, 3, 4, 5, 6. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is correct. Okay. That's to be expected. That 1, 1, 1, 1, 2. Okay. 1, 2, 1, 2, 3. Okay. That's so then. Yeah. Okay. Okay. Let's just write a brute force. Okay, I'm like going all in on this problem, I think. Brute. I'm legit just going to write an n to the 4 brute force. This is going to be so stupid. Okay. Let's at least write like an n squared. Let's write this. This is depressingly bad. Okay. Let's at least write like an n squared or something. Right? I said n squared was simple. I forgot. I didn't. Okay, I should really be writing these down. Wait, I printed these out and I didn't even grab the. Oh my god, I'm bad. Let me go do that. Okay. Let's try that again. Right. Yes. Writing things down. Helpful. It's 3 pages per one of the poems. Okay. Pencils. No. Pencil. Right, okay. So it was what? Okay, so what's our n squared? Our n squared, fixed left and right. Move one occurrence elements. And then just add them in as you go. It's not that bad, I think. Okay. Okay, so that means if we're using okay, well, actually it'll be easier. Let's include the counter. Sure. And then two.
minus I is greater than, yeah, so then if we have a valid sized range, check. Okay, so we know I is valid, so just check that. And count age is equal to 1. And so plus equals count minus 1. Because we have to get rid of that AJ that we just said. Okay, we need to fill. Okay, let's put this in a solve. Alright, this still runs, does not run. Need a capture. And this is still 9. Yeah, okay. So now let's. Okay, wait, does this. 16, okay. Let's see how it is. See how it is. Should be minus 2, but you don't get rid of AI as well. Okay. Okay, how big of a case am I willing to debug here? I think like 6. I'm very lazy. Heck ton of cases. Okay, let's use rand because I'm also lazy and I don't want to make an actual good array. Yeah. Heck, okay, I'm lazy. I mean, the program will terminate right after anyway, so it doesn't have to print 1 or 2 extra things that are long. I don't know why I care about formatting on literally like debug printing here, but too bad. See out the end line, and we should also see out answer and the answer. So and run this, and it fails immediately. Okay, why do we have -2? How is my answer getting -2? Okay, that's bad. How the -2? Oh wait, things need to be initialized, don't they? So what do we even have here? We have an n. Okay, n gets initialized. A gets initialized. Prefix position up in the segment tree gets rebuilt. Alright, it gets completely rebuilt. Lazy does not get set. Lazy should be getting set. Okay, so we need prefix and position to be cleared out. Actually, prefix doesn't even need to be cleared out. It gets it's self-initializing. Okay, position. Okay, let's see if it still fits. What? Did it really just run through all? What? It's not finding anything. This is responsive. Huh. This is strange. And yet, all of these are failing, so... Let's see. I didn't change anything significant either, did I? Like, I initialized lazy. That's like basically it. I initialized lazy, and I filled these. But these are all zero initialized. That should not be a problem. Which means, unless I'm misunderstanding the problem, that's a significant possibility. Yeah, I mean, it doesn't look like it's catching anything yet. Okay, maybe we'll resubmit. Maybe I fixed something without realizing it. That makes no sense, but... Right? Because... Otherwise, that just means my brute force is also wrong. Which is a possibility, because it's not really a brute force. Yeah, okay, so that means my brute force is also screwed up somewhere. Which means that my general methodology is just not right. Hi, I'm taking Plat right now. Okay, let's see. So what if instead we do other things? Right, okay, so let's literally write that in for into the for brute force. From what I was talking about earlier. Like no thinking involved. Just take a brute force and just smash the problem. Okay. Okay, so this is good. Right, this is literally as brute force as you can get. And then running this many tests is probably going to be fast. Okay, here we go. Here's something. Oh yeah, well, it would have been super easy to just assert that your answer isn't negative. Okay, let's see. 5, 5, 1, 1, 1, 3. Getting negative 1. That's bad. You should not be getting negative 1. Let's see. It's been an hour and a half on this phone already. Alright. Let's see. How is this? 0. Oh, I see. Oh, so that was probably the issue with my brute force, is we don't set things to 0. Oh, that probably explains why I didn't get caught for like 1 through 4, because like those, okay, cool. So we only care if it's 1 or if it's 2. Right, so now I should get, okay, get 1. Is 1, no, 1 is not correct. We should not be getting 1. 2. Okay, that is correct. Oh, where are we getting the answer from? We're getting the answer from these 3. Okay, let's see. What might work is if we just do this. Let's see if that actually works out, though. Okay, and also, yeah, so it looks like, yeah, so let's do 50. Maybe cut down the zeros. And comment these back out. I really miss my debugging template right now. Okay. And run. And it dies again. Okay. So this. One five three five two. 352. Yeah, there's only one. Yeah, there's only one option here, but we're getting 2 of them. Okay. So let's make the tester back out. What? Okay, so what is this supposed to be? Okay, so the answer definitely should not be 2. The answer should be 1. Okay, prefix will probably be helpful for this one. Let's actually shift this down closer so I don't have to scroll as far. This. Okay, here's 1, 2. 1, 0, 1, 1, 2. Okay. Yeah, that's the right value. Suppose let's do this. So okay, so what is val? Val is like the answer. Like this is the left and right. This is how we would get. Wait, why is this val 1? Shouldn't this val be a 0 since we don't have enough actually do make the thing? Also, st without val can be 0. No, but then count will also be 0. Okay, that's fine.
No, that's actually no, that's fine. Because I'll be assuming. Okay, yes, that's fine. And this 2 here, that's also. That 2 is a little sketchy. Should not be 2, should it? Should be okay. No, because we're assuming we could have chosen what? We're assuming these are different from that. Huh. That's a little. No, that's it should be just 1, I think. Okay, in any case, these don't matter because next is only 1. So now next is 3. So here we go. Here's the thing. So, okay, so we're creating now 2. So this range over here. Wait, why isn't it 3 then? Oh no, so creating plus 2. Alright, so just creating this. Yeah, so this should not be 2, it should be 1. So where's that extra one coming from then? Oh wait, oh, so this entire range should not be bumped. Just this range should be bumped. Okay, so that means we need to actually push n twice. And then this should actually end this one, so that's it. Okay, so then should we push? There we go. Go. Didn't crash immediately. Progress. Okay, so should work. Hopefully, maybe. Unless this brute force is also flawed, which you never know. Okay, let's give this a shot though. Whoa, we got more than the sample. That's pretty epic. Got TLE. How are we getting... Wait, oh, I'm printing the brute. Oh, I'm stupid. maybe don't run your into the fourth brute force. Okay, so I'll finish letting those verdicts come in. But it should, I mean, like, the brute isn't catching anything. Which, I mean, the brute is randomized, so, like, there's probably some edge cases which it wouldn't catch. But, yeah. I mean, I am running, like, a lot of tests, though, so should be able to hopefully catch most of things. Okay. Let's just let this finish up. And let's make sure we have
Just like this. O 9 and okay, I have solved a flat problem now. In contest. I am cool. Yes, okay. That's very narcissistic, but too bad. Alright, so that's done. That is done. Done, done, done. Bye, bye, bye. Okay. Right, this one, yes. This one is scary. Because we're like, I don't know what we're doing. This is weird. It's scary. I don't want to do it. I don't know how to do it. I want to do it. I don't know how to do it. Okay, let's see. So we can get n is less than 6 plus maybe the k0 subtask. Then that is, I don't even know what that is. That's not bad, right? That's 7 out of 24. It's less than a third. It's like, maybe we can't do math. Wait, it's like less than a third. It's going to, wait, no. Looks like if we had, okay, I'm actually bricking maths. I'm literally bricking fractions. This is sad. 3/8. Yes. No, not 3/8. 2/7. I don't know. Whatever. It's not that. It's not that big, but it's good by my standards. Right? Because I bet most people probably solve the first problem. Okay. Yeah, but like, yeah, the first one doesn't seem that hard. It's just bash ds. And the way I solved it was probably not that, like, oh, here's when I use define. Yeah, the way I solved it was also probably not that elegant either. Okay, but I solved it. That's what matters. Okay, next one. Okay, this is scary. Right, okay, so what if we pair, right, because there's like, okay, so given a graph, a directed graph, how many different ways can you get from one node, from one specified node to another specified node? And does that run if I cube it, that value? Right, okay, so let's see. So you can visit, so it basically ends up being like a permutation, right? Because you could end up, because if you have like all the edges, well, I mean, okay, so you don't actually have all the edges because k is small, but like, let's assume worst case you have like all the edges, right? So then you could end up basically going in a permutation, I think. Except then you, wait, no, but you'd also loop around a bunch. So, but you can only do that twice here. So you would do, so you could go and some permutation of n, and then loop back, do some permutation of n, then loop back and do some permutation of n. Well, no, you couldn't. You can't do permutations because permutations are probably going backwards. So, okay, so it's actually 2 to the n, right? Because you can choose to skip or not skip. And then you go back, and you can do another 2 to the n, and you go back to do another 2 to the n. So that's 2 to the 3n different ways. And then we're cubing that because we have potentially three different pairs. So that's bad. It's not good. Right? But we can't, but that's very, very worst case, right? Because I don't think that will actually happen.
Well, that could actually happen. Right, yeah, that could actually happen. I'm taking Plat right now. What's happening? Platinum contest. Yes.
Bad communication. Should have. Parents are like taking a nap though, so I'm not gonna wake them up. Just told them like I'm doing the contest. So yeah, whatever. I should have told them though. Okay, let's do it now. Okay, so we were right. Yeah, so there's 6 because then we have 3. So there's 2, but wait, there's not even 2 to the end edges. No, but wait, but that's not the problem. Because there's different orderings of the edges is the problem. Wait, this is even worse than if we just took all the edges and then just permuted. Wait, no, it's not. That's 36 factorial. No, it's like 18 factorial. But that's not better. Maybe we could do a thing with like bit mask because there's only okay. So how many edges are there actually? Because you can't have an edge to yourself. So we would just have it's like a 6x6 grid, except we would have 5 plus 4 plus 3 plus 2 plus 1, right? So that's 15 plus k, just up to 2. So we have 17 different edges at most in our first subtask, except for this friggin' thing and this friggin' thing. Okay, whatever. I'll hardcode that? Question mark? I don't think I'm allowed to hardcode that. Just be like, I don't know. Although those are k equals 0, so maybe I can just get a k equals 0 solution. Okay, so then with that, okay, wait, so then, yeah, so it's 17. So then we could do, that is bit mask deep, well, no, because then once you have the ordering of the edges, you need to be able to, right, because it's actually 2 to the 17 times 17 squared. And that's actually, no, I think that's doable. Yeah, it's definitely doable. Yeah, so then, and then we also prune a lot because because a lot of the edges will not be, they will not be, like valid, right? Because you can't just have like 2 random paths and just be like, or 2 random edges, but like stick them together to make a path. So that does prune out a lot of stuff. And then the other question is then how do we need to decide like when one path ends and another path begins. So then we can say we are currently on. Okay, so then we do 6 times. Okay, here. Wait, I have paper and a pencil. I should just write these down. Okay, here, routing schemes, right? So we have what? So we would just permute through all the different senders and all the different receivers. There's almost 3 of them. So we have 3 factorial times another 3 factorial to permute senders and receivers. So senders. How do you spell receivers? Is it IE or okay, that's EI? Stupid English. Senders and receiver perms. This is an S. Okay, and then we have a bitmask DP of 2 to the 17 times the 17 squared times 3, right? Which is saying this is the current path we're on. So this ends up being 6 times the 6 times 2 to the 17 times 17 squared times 3. And that is too big. Okay, so we need to cut a factor out of this. Wait, this is actually not 17. We can actually get away with, instead of 17, we can do 17 times 6. Because we don't need the entire path, we just need to know which node it was. So that, yeah, and this is all completely worst case. Which means we can probably, that should do it, I think. DP is pretty fast as well. Okay, should I just do that then? So we do iterate, okay, so do all the permutations of the senders and receivers, then do a bitmask DP where we store which edges have been used, and so which edges have been used, the current path that we are constructing, and the current node, and the last node that was on the path. And then, yeah, so we can either, yeah, okay. Oh, this is still a little too long. Is there some way you can speed this up, maybe? What do we do this without doing all the sender receiver? Okay, so for sender receiver permutation, we know. No, we can't. We can get rid of one iteration, maybe, I think. Um, Node may appear more than once within the same path. Oh, right, and this sometimes an extra 20 because we have 20 test cases. Okay, this is not going to work. How to speed up? Ugh, I literally don't know. Okay, let's try this one then. Right, yeah. So the gold problem 3 was just like make an observation about the triangle and then do a Cancer DP with geometry on it. So this one might be similar. Let's see. Yeah, so now instead of triangles, we have squares. Epic. Square cells. Oh, rectangles. That's. Whereas we have like a rectangle, except then it also. Oh wait, maybe not. They're not. These are not rectangles. Okay, no. So we have like a base rectangle, and then it extends outwards. Like you can extend each edge outward. Like yeah, like you can make it longer basically. Right, and the size of the rectangle might just be one cell. Okay. Wait, so what are we asked to do? Count the number of balanced subsets. So we can choose. So okay, so we count the subsets of the thing. Okay. And for half credit, you can iterate through every single subset. Oh wait, right, yeah. So okay, so you can't move all or not move. Uh, you can't extend. You can only extend one vertical edge and one, or on each side you can only extend one vertical and one horizontal edge. Number of balanced subsets modulo 10 to the 9 plus 7. So maybe. And rectangle, oh right, the rectangle must be filled. Filled rectangle. So you make a rectangle, you fill it, And then you could extend each edge. You can extend for each side. You can extend one of the two edges outwards. Right? Okay, let's write this down. Right. I feel like this is okay. So just like counting. Well, duh, it's counting. No, really. But this should be doable. Right. So can we? Okay. So we can iterate through every single possible rectangle. Right. How hard is that? To iterate through every single possible rectangle, it is what is it? What is it? Right. So we could. Okay. So wait, how big? Neighborhood order pairs ij. Okay. So cool. So the grid is small. So we can just go through like. Wait. This showed up in a silver problem. When I was just counting the rectangles, we have to actually find each rectangle, I think. So, okay, so we can just iterate, we just like an n to the 4, right? We just have we just go to all the x's, all the y's, and just be like, okay, and then there was an extra, okay, so it's n to the 5. That's a little, yeah, that's not gonna work. Okay, but it's n to the 4, and we can do some, we can do the column optimization stuff. So that gets us to n to the 4. That's still not good enough though. Okay, let's see. So then, wait, okay, so for the half-credit subtask, can we really just iterate through every subset and just check it? Right, because 2 to the 20 is like 10 to the 6, right? And then we would just go, I guess the hard part is actually how do you implement the check, right? So to implement the check, we would... Okay, so we can run a DFS to check condition 2. Condition 3, we can put each, for each thing that exists. Oh, what we can do is we can sort the cells. We can sort a subset of cells. And then everything should be, and then we have all of the cells of the same column and stuff together. And then we can sort it again by row, and then we have all, okay, so that's 2 to the n times n log n, I think, because the sorting will be the dominant factor there. 2 to the n times n log n. 2 to the 20 times 2 to the 20 times 20 log 2. I don't have log 2. Okay, what's log 2 of 20? That's like 4 point something, because it's 2 times 5. Right? That's squeezable. Wait, is that it? So that gets you half credit. Does that actually get you half credit? Feels sus. So I remember missing something in the triangle problem, so maybe I'm missing something here too. Okay, so that gets us half credit. Go through. So go through each subset. Do fast for condition 2. Okay, condition one just set as we do the subsets. And that's 2 to the n times n log n. Okay, so we have that in our pocket. So we can probably implement that. I might need to implement that regardless because I'm pretty sure this is gonna. If I do come up with a full solution, it's probably gonna get buggy. Okay, let's see. Full solution. How would we do full solution? Okay, so we want to. Okay, so we need to find a way to iterate through all of the filled rectangles. How to easily iterate through all the filled rectangles? And right, we don't actually we might not necessarily just do, so we can have like a tower on top. So it's like a bunch of connected rectangles, kind of. Except we can only have, so we have one big rectangle and 4 small rectangles connected to it, which might be empty. Right, so how many rectangles can we have? We can have, right, because it's not that hard. So you can fix one, so we can fix the top left of a rectangle, but then just iterate. Just go to the left, and have height 2. Go to the, or going to the right, right? Okay. Then so how many rectangles would that end up getting us? Right. So we can have 150. So what's, okay? So let's do like a 15. Right. Yeah, it's big. Okay. Right. Because we can have 15. We have 15. Right. So that would get us, yeah. So we would have 149 plus something like. Basically, we have O of n rectangles times n. Wait, we only have n squared rectangles then. Well, yes, we don't have. What am I doing? We only have n squared rectangles because there's literally, because that'll just be our top left and our bottom right. Yeah, so you have n squared rectangles. Okay, and then on those n squared rectangles, we can get more rectangles. Right, we can like stick an extra thing on it. And stick a thing on it. Yeah. Actually, our rectangles might go side. Okay, so it's actually a little more complicated. So let's see. We could have, right? Because we have a rectangle like this, and then we could have like it stick out like. Actually, no. That would just be a different rectangle. Okay, that's not a problem. Yeah. So it can only stick out within the boundaries that we want it to. Okay. So then we need to count those. How many are there? How many are there of those? So okay, so we have, okay, so wait, let's do this. We have n squared rectangles, right? Okay, and then we have to find the things sticking out the rectangles. Right, so again, we can do, okay, so n to the 4 is a little too high here, so we can't do n to the 4. So we have to find each of the, for each side we have to find the rectangles in O of n, right? Wait, this is a classical problem, isn't it? We find the number of rectangles inside a grid. Okay, so we know the bottom, so then we just need to find. Right, so then what we can do is we can iterate through each height. Okay, so let's just assume that like we're looking at the top of the rectangle, right? So then we look at each height. We just iterate left to right, and we do the whole n squared over 2 1 thing. right? Yeah, this should have been a silver problem. I was literally teaching this in our competitive programming club, where so we go across. Yeah, so that's n, and that takes O of n, right? So then we count how many of those there are, and count how many of the next ones there are. Right, and then we just need to make sure that we don't count it if, and then if, yeah, we need to make sure we don't count. Okay, so let's see. We have okay, and then right, because then otherwise we are overcounting that rectangle because it conflicts with others. Okay, is that it? Does that handle everything? And I add one for no. Okay, let's give this a shot. So how are we given these? We're given these as a grid. Do we want them as a grid? Yes, doing a grid is fine. Yeah, let's just do it like that. Okay. When you all right, so we need multiplications. I'm going to need long ones. I'm currently sitting backwards on my chair and just like leaning forward, which is probably a bad idea, and it is probably going to hurt my back, but I don't really care right now. So here we are. Right. So we have we have this. Right. Okay. So now we need. Okay, so how do we do this? So we need to check. Okay, so we do end up needing, but this should end up still being n squared, right? This is a little sus. Because because there are only n cells which contain graphs. Right, and then as we iterate, we'll stop. Yeah, so even if it might actually take up to n cubed. I don't know, I'm bad at complexity analysis. But in any case, because we are, because that only happens, we can only deal if we have a full rectangle. So there's still only n squared full rectangles. So we're fine, I hope. I think this will run in time. In gold I had a thing that ran in like n to the 4, and n was like 500 or something. So this, okay, that's a completely stupid example. It has absolutely nothing to do with this, but whatever.
Okay, so you know, 2 is equal to 1, and C2 equals C1. Right, okay, so now we need to check if this is a rectangle or not, and if it's not, then we need to stop, and okay, let's see, so
how we want to do, so we're extending down the rectangle, right? So
in right, so we have to stop at max column.
right, and then yeah, okay, so that'll clean itself up.
Okay, and then now, okay, it's going to be an int. No, yes, it can be an int. Okay, let's see. Can I do this in a non-cancer way? I don't want, okay, no. Let's just bash the cancer out. Okay, so let's do the top. So for the top, we want for h equals 0. No, height is 1. Okay, comma's useless. Height less than 10. Right? Because we can't, because we already have an existing thing, so we can't have height go more than, height can't be n, because that means that we're using n cells at least, and we can't use it because we already had, we have a rectangle already which has cells in it, so that doesn't work. Okay.
Isn't this n squared? Wait, how did I say I was going to do this in O of n? Shoot. Because I remember the Silver editorial, because I was when I was going to present it, I remember reading the Silver editorial, and it says something about how you can do this in O of n, but you don't, but it's not necessary for this problem. But it is necessary for this problem, so that's bad. Maybe I could just pray that we won't have to, because like it won't actually be that big, because like n is like, because n is also bounded by like the number of because like the number of cells is also bounded by n, and not just the grid size. So yeah.
Right, because this is what? This is 150 to the 4th power, right? Because there's n squared rectangles.
And then there's there's n squared rectangles, and then we're doing another n squared times 4 for each side. Yeah, I mean, like, I think it should squeeze, but not, but they're kind of close, right? Okay, let's see. How can we prune this a little? Int rect size equals 2 minus S1 times C2 minus C1 plus 1. Right, so now we can make this equal to minus. Right, so anything after that will not work. Okay.
Right, actually, so I'll start at 1 because we have that empty rectangle. Actually, wait, we could probably do this in O of n. Or not O of n, we could at least do this faster if we actually stored things. Wait, actually no, we can do this in O of n with the monotonic stack. Yeah, let's do that. Okay. Nah, I think we don't actually need box size. Okay. Use STK because I've started to use ST for my seg trees. And I want to mix those up if I use both of them the same thing accidentally. Okay, so what we do here is we need to store the height, so we don't actually, because it ends up being O of n because like we can only go up the amount that there is. So like that doesn't make any sense. But I'll just do it. Okay. Also, I kind of want to just transpose it, or not I want to shift everything. Let's do that. Right, and then that way we don't have to worry about ray boundaries at all. And then I'll make this times 3. Right, so for the height, okay, if right, so you keep going. Okay, so just need pair for the stack. Oops.
Right, and then, oh yeah, this actually works out nicely as well, because then everything doesn't go into S. Yeah, so we'll actually have to handle, yeah, so we'll handle, yeah, so we'll handle anything left in the stack separately then. Okay, so cur, plus 1. The width is okay, so our width. Okay, so it's our width. And then our rectangles is right. It's width, and then we so you can choose. And we can choose another. Wait. Okay, so we can choose. Okay, so we can choose the same one again. Alright, so you can choose width. Okay, so we can choose W different rows to be our first row or to our first column, and then choose another W to be the last column that we include. Wait, what? That does not line up. I think it's n times n plus 1 over 2. And the plus 1 is for all the size 1s. Okay. Times. Wait. I feel like what we should have done. Oh, yeah, okay, so what we're actually doing is the width is actually no plus 1. What if it's the same height? If it's the same height, we can just ignore it.
Okay, so you can actually move, oops, move this into a function. Oops, no, no, no. Right, and that shortens the code by a lot. We should do that. Oh, if we actually pop from the stack, that might be helpful. Just do min max. Because if it's equal to the min, then we have to get rid of one of the widths. Or no, we can just minus one at that. We can just minus. We'll just minus the height because it's only one fifth. Alright, so more. Okay. Why did I do this? Why did I do BPM and not bottom? Do I have to check mod? Yeah, I have to check mod. Okay, whatever. Just be lazy. Just do mod at the end. Okay. Oops, did I write this in routing schemes? Yes, I did. Okay. Oh, geez. Oh, that's why. That's why like all these are coming from. Cool stuff. Right, okay. And it's wrong.
Wait, there's legit more subsets than that exist.
Right, this should not be addition, this should be multiplication. Oh wait, this might be a little annoying. Okay. Mod. And it's wrong. Well, this is sad. Okay, that line's up. Wait, what? These are all starting as 1. How does it not... It should at least return 1. Huh? So somehow we're getting negatives in here. Okay, 0. Okay, so why are these 0? Bottom is 0. Why is bottom 0? Bottom, stack. keep forgetting I don't have input copy pasted. Okay, 1, 2. Height 1, column 2, right? Okay, that lines up. And that's it. C minus that would be 0. If snap process minimum, then minus the size. Where is this 0? Should be max plus 1, right? Because yeah, for the other one it shouldn't have been, but for this one it should be. 17. Well, I think it's double counting. Yeah, you can double count this. Shoot, I did not think of that. Frick. Frick a stick. So maybe have a restriction where the height of the outside. No. I really don't know how we would. How would you handle that? How did I not think of this? Okay. Okay, so stick some condition in this. I guess we like strictly less. Actually, wouldn't there for each side that exists? Wouldn't that be a chance? Wait, I'm also kind of stupid. It's not. We could have right. It's not just a rectangle. Okay, wait. Yeah. Okay. This entire approach is like completely flawed. Because we could have. It's not necessarily just one rectangle on top. You could have. It's like anything sticking out on top. That would work.
Okay. Yeah. Yeah. This is screwed. This is screwed. Okay, let's just implement the brute. Brute. Okay, so this is 995. This is 917. That would be 75 or 78. 78. Okay, here we go. Okay, this 7 times 3. Yeah, actually, let's keep that around just because it might be useful. Okay. Actually, wait, we'll be storing these now as a list of points, not as. Okay, so. Okay, so okay, wait, so how I want to do this then? Okay, so what if we create 2 to the n vectors? Does that take? Do you think that might take too long? Okay, so let's not create a vector. Let's do like a fake pseudo vector.
Okay, so how do we do this?
Honestly, maybe just do a DSU. Actually, no, because that would require we don't actually have like, store edges and stuff.
Okay, I'll just have to go with the DFS.
Now we can do a DFS.
So if the x coordinates are the same. Okay, right now I need to actually write the DFS. Bound. Small. Fixating from XY. Okay. That should do it. That's bad. Oh wait, I'm doubly bad. Okay, this n doesn't even. This n. Oh. Fuck. Okay, I'm stupid. Okay, so this n does not have anything to do with the number of grass in here. I don't. Why did I think that? Why did I think that? Why did I think that? Okay. Well, that explains so many things. That explains very many things. Okay. 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 This is sad. Okay. Yeah, that explains many things. Actually, no. Yeah, okay, so that explains why, yeah, because it didn't make much sense for a brute force to be half subtask, or to be half the test cases. Alright, so this will only get 1 through 4. Okay, that's still fine. If I can get the first subtask of this one and the first subtask of the other one, I'm doing really well. Let's get 6. Okay. Alright, okay. Okay, desubset. That's just me. Why is it? Alright, it's printing 3 times. Yeah, okay. Okay, so the first two. For some reason, don't match up. am confused. Okay, this should work, but it's not working. Does it say all false? Okay, wait. I'm confused. What? Zero, zero, zero. I'm confused. Don't get why this stuff. Find. Should be finding. Huh. That's not good. Wait, no, it's just because I'm printing it. Shouldn't this literally... What? I am so confused. Why does this not work? Okay, legit. I'm going to just... Oh, why is that? Yes, 2, 3. It's literally right. Oh my God, what is going on? What is going on? Does lower bound like not do what I think it does? Current is sorted. It's sorted. I sorted it with comp x. Is comp x not do? Did I screw? Yeah, I screwed up comp x. Okay, I'm bad. I just okay. It's like doubly screwed. What's going on here? Okay. There we go. This will probably... Well, this should not TLE, because if it TLEs, then I actually... Well, it's going to print a whole bunch of debugging. Okay. Let's just get this. This will get 1/5. Let's see. I am hungry. Okay, it's wrong. Yeah, it's fine. I don't care what the verdict is as long as I got what they needed. Okay, cool. Okay, I'll probably say like 366 or something like that. Okay, considering. Right, okay, I don't even know how to brute force this, I think. Yeah. Okay, I'm going to go get dinner. Come on, Jackie. Okay. Cool. Got some vegetables. Right. Yes. How do this? How. You literally can't solve n is 6. Let's see, what about
How do we just brute force recursively, right? We go and we're just like, okay, let's say we end this path here. So if you keep track, so you have to remember where the path started. And so yeah, that can be easily done, right? We start where the path, you just keep a note the path started at. So we would need to keep track, let's see, we need to keep track of, so we need to be like, here are the things, the stuff we would need to go. Okay, so we have the last. So if we were to get rid of that 36 factor, that would be enough. But how do we do that? So we can replace the 36 with the 64, but doesn't help much. No, actually, we take out the 3 as well. No, we wouldn't. Actually, we would have another 3 because we need to start which one was what we're doing. Winds blow, wind, wind, wind. Ugh. I legit cannot solve n is less than equals 6. This is depressing. Another may appear more than once within the same path. Now the number of distinct varieties such as each for a second. I think, wait, you can't actually have 17 edges. Because you could only do, like, with all edges of size 1, you go back The other edge is size 2. Yeah, there's no way you can actually. So that probably is a stricter limit on number of edges you can have. Right, so that actually cuts it down, so you have what? You have 5. 5 plus 4 plus 3. Yeah, 5 plus 4 plus 3. So that's what? That's 12. 2 to the 12. That's more approachable. Right, and then we had what we had was like 6 times 6 times 2 to the 12 times 12 times 6 times 3. Okay, let's write that out. What is, or not write it out, let's multiply that. Paito 3. Okay, 6 times 6 times 2 to the 12 times 12 times 6 times 3. It's angry because I didn't actually. Okay. 6 times 6 times 2 to the 12 times 6 times 12 times 3. That's 2. And then times an extra 20. That's 6 times. Wait. Yeah, 6.3 times 10 to the 8. That's a little sus still. Just a little. Can we prove a better bound than 12? We're like, I don't think so. Actually, wait. 12 is, we would have 14, not 12. Because I forgot about the K. Next, you have 1, 2, 3, 4, 5. Okay, that's 1. You have 6, 7, 8, back 9, 10, 11. Yeah, we actually probably have more than 14. Ugh. Okay, I'm gonna shut one of the windows. Okay, so what if we construct these in terms of paths? What if we, okay, so if a path has one of the k edges in it, then we split that path into separate paths, right? So now we have up to 5 paths. And so this becomes 2 to the 6 to the 5, which is 2 to the, okay, that's still bad, okay. There's no case which has a lot of edges. Maybe there's a better bound that I can't, it's not seeing. Alright, so what is our current? So you could do n over 2 factorials squared times 2 to the e times n times n over 2. Well, it would be at least enough to solve the samples, right? The samples are all, well, okay, no, this the 13, 7 factorial times 7 factorial will probably be too big, right? Oh, wait, no, that's not that. But then you got like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 2, 10. Okay, it might actually be doable. Wait, what is considered, what makes them distinct? Have I been reading this problem wrong the entire time? No, yeah, it is by edges. Okay, so that was, okay. So we want some sort of
Okay. It's just times 20. 8. It's 9 actually. No, 10 to the 8. It's another times 7. We can't pass the first sample. Okay, I see some better way to do this. I mean, duh, obviously that would be the solution, but I see some less crappy way to do this. One square first. My brain is fried. It's don't know how to do this. Okay, I'll go grab like more. Okay, let's see. Grab some tortillas with cheese and bacon. Very yummy.
With some node I can only have at most k plus 1 paths to a node j where j is greater than I. Okay. Since that means every most 3. Well, no, not necessarily. Well, actually, yeah, because otherwise you can't use them all. So each node can have at most k plus 1 outgoing edges and k plus 1 incoming edges. Okay, and that's, yeah, so our lower bound is now, or upper bound of edges is now 14. Wait, and the in degree of a node has to be the same as the out degree of a node, right? Or not exactly. So like the in degree, but if it was, okay, wait, I should be writing these down. Right, each node has some in degree and out degree. minus v equal out to be So that cuts down a bit more on our bounds, right? Because instead of 14 now, because these are ins. So E is what? What is E? M times n minus 1, 2. Minus 2s. Yes, that would make this feasible. Actually, I'm not sure about this k plus 1. That doesn't seem right. Yeah, that's not right. It's k plus s plus 1. Where's k plus s? K plus s. Okay, I think this should work then. It's going to be cancer to implement though.
Okay, so how do we actually implement this?
Okay, so let's see. The DP. Alright, so I have to go through each permutation, right? And then we have our DP. So I think the main part is just going to be how to spit masks with the edges, because that's annoying. So that can be we can just give the edges each a number, and then just have a separate array of edges somewhere on the side, and then what do we want? Okay, it's even an hour. We have 1 hour. Okay. Wait. Okay. So I'm not gonna get any. I'm not getting anything else on this problem 3, right? It's just. I'm just not. It's just not happening. Okay. So. Okay. So this is it. This and maybe a K equals 0 if I'm lucky. Okay. Let's turn the light on. Man, I've done like 11.5 hours of contest. Actually, no. This weekend I've done like 14-ish hours of contests so far, I think. Maybe 13-ish, but it's been a lot. I'm kind of burned out. Okay, let's see. That doesn't matter, though. At least not, it does matter, but it's too bad. Okay, let's see. I can't type a 0. That's not ideal. Alright, we have freaking... So I perform a here to bit string. Okay, so
Oh, she has to be. Just use.
right, let's just give 20 is already probably too high. Okay. While, all right, we were going to go and we were going to be like, okay, let's just rewrite this. Right. Receive. Jeez. Running out of orange juice. Okay. Wait, center should even sorted order. Okay, do why answer plus equals count things. Okay, wait. Okay. Okay. Okay, so that's a six factorial squared. Okay, that's that out of the way. And now we want to print the answer. So now, okay, we're saying for this certain, what's our current? Okay, so we need a dp. Let's just go straight up. Let's do like 18. What the heck is happening in the room above me? Okay, so that would be our mask for the edges. That we need max n for the last node that we visited. Wait, I have this written down. I don't have exactly written down. Okay, let's do that. And then, okay, so then we have 3. Should technically be mn as well. Mn over 2. If I do 20, I think but even 18 might take too much memory. 18 is what, like 10 to the 2 times 10 to the 5, right? Times 100 times 50. 2 times 10 to the 5, 2 times 10 to the 7. Yeah, it's 2 times 10 to the 9. That's bad. Okay, let's just assert and this lesson equals a sample, so I'll just sample 13 and it's less than equal to 13, and now we can just make this like 15 or something. There. Beautiful. Right, and then 2 times 10 to the 5 times 15 times like 8 should be well within. Wait, 2 times 10 to the 5. Oh, that might actually be a little close. Okay, let's just chop this by 1. I mean, if it's more than like that, it won't work anyways. Okay. It's a double do while. Beautiful. Okay, now we need to go through each edge. Does it matter which order we go in? Right, so it depends on strictly before. Also depends on strictly before. And then another time, it just doesn't matter what order we go in. Okay, yeah, it should be chill. We just go in this order. Hi there. Thank you. Okay. Case listing. And here this is because with case S actually. Yeah, because we permuted center. Okay, cool. So that's done. Now we need to go through our next one.
Why are you talking to me?
Because I have a recording, so I'm like recording what I'm thinking. Okay. This is like, why are you talking to nobody? All right. Well, I suppose it does sound a little weird. It's here, kid rambling to nobody. Okay, let's see. So now, oops. All right, so now. Now what? Okay, so now, right, this should not be N, this should be M. Okay, so if this is already in the bit mask, okay, I should give these more meaningful names. MSK, good enough, mask, right?
mask. What is J? J is node. Okay, I'll use U for node. K, what is K? Okay, so this is sender, so use S for sender. Actually, it should be a sender index, so okay, I'll use I. Alright, and then next, okay, so this can actually just be E. Or no, I'll just put this J. Right, okay, so if the mask, right, so if it's already in the mask, we don't want to do anything. Well, what's our base case here? Our base case is if we have used, okay, oh, right, we need to, okay. Right, I need to actually initialize the DP as well, since, oops, that is not what I wanted, since we do use it multiple times. Okay, so let's do DP mask UI equals 0, and now we will start with no edges at node. Ooh, that's a problem. What node do we start at? Because do we just start any node? All the nodes. We could start at all the nodes. Actually, no, we couldn't. No, we couldn't. We would start at sender 0 and I. What is I? I is a sender. We're at 0. This one. Okay. Okay, if edge j dot first is equal to u, then that means that that could extend our current thing. So we would say dp mask or j edge j dot second. And we'll just stay with the same I. This equals. Okay, do we need to do? Yeah, we need probably. Actually, I don't think we need mod here, but just in case, I'll just do. Okay, so I'll just make an add function because I don't want to type this over and mod it. What are we adding? We are adding dp mask UI. Okay. Right, so that's okay. So that's extending the edge done. Otherwise, we cannot extend. Okay, whether or not we can extend the edge. Okay, so we only. So then, if this new edge. Okay, so if u equals 0i, right? Then that means we can start a new thing. Otherwise, we cannot start a new thing. In which case, this edge will just be unused. We just can't use it. Right, so if u is receiver I, then dp. Actually, maybe this wouldn't even. Yeah, I think this would actually just not be. Well, actually, we could probably speed this up a little then if we include an adjacency list, because then we only need to do right. We only need to do this because if u is not because we're not at the end of our current path, we can actually so we can actually speed this up a little. We get rid of a factor of m, I think. And then we replace that with a sum times a mask. So it'd be m times mask and m times s times mask. Yeah.
Right, so yeah, so let's do that. So how do we do that? We would want a set pi. Actually, do we just set int wait, no, we still need to. Actually, yeah, this would be if. Yeah, so this would be. Okay, so let's get rid of this. Okay, so how do we write this here? Close out the window. Okay, so I have like 40 minutes. Yeah, 45 minutes, okay. Okay, actually, theoretically, that should be it, I think. What is this? Routing? Something doesn't. It's not in this code. Okay. That's bad. Hmm. Right.
It's just taking a long time to run. Oh geez. I mean, 5 is pretty big, but it's not. I mean, 5 factorial is not like that big. Good. Oh, it's just taking a long time. Okay. This thing needs to run faster.
Times 2 to the what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 to the 10, it's 11,000. Into the 7-ish. Times 13 times 5. Yeah, 4 times 10. Wait, 4 times 10 to 8, that's just 3.
But I actually don't need to permeate the centers, right? Because that doesn't change anything. This is a set of paths, yeah. Okay. Okay, what's going on? It'd be helpful if I actually put in a dp value. Okay. Not right.
Like a half hour. What is going on here? Okay. We can't take. How are we taking? Oh, we only want to go one direction. Hmm. I think that is right. No, it's not transitioning to the next. Yeah, I think we need. Yeah, so this. Uh, okay. Cool. No, I'm gonna go to the restroom and grab a fork and put away this plate.
Okay, back. Let's see. Yeah, that looks like just about what I expected. Okay, at 23 minutes, just squeeze as much out of this problem as possible. Let's see. Let's get 6 and 7. K is 0. Let's see. K is 0. K is 0. Let's go to the assertions and just pray something happens. I don't know. Actually, I still just be wrong. Oh, it'll still crash, apparently. Okay. So this one we have. Yes, it's like 430 something. Maybe 450. I'd be surprised if that's how people solved everything. Okay. Okay, so K equals 0, so we can't go backwards. I don't know what I'm doing. There's no way this is going to get anything else. Especially because it's multi-test, so it's not like you can choose one easy test case. And apparently, memory limit exceeded. And feels bad, man. Okay. Oh, now my disk space is critically low, which means this recording is probably going to die. Let's see, how low is it? Okay, this is a big bro. Okay, fine, I'll just put this back. So I think this could judge your last submission, so I need to make sure I get those points back. Let's see, how much? 3.24 gig. Yeah, that is not ideal. Okay. And yeah, of course, this is not going to get anything else because why would it? So now, so we can only go forward now. Okay, so this means, okay, so in every, okay, where was that? Okay. Every sender can only will have exactly one outgoing edge and exactly 0 incoming edges. Every receiver will have exactly one incoming edge and 0. Wait, no, I think I had a solve. Okay, whatever. I know what I mean, and that's what matters. And then, okay, how's that help us? So then we can shift it along. So that counts as 1. There's only one we can do those. So only one we can do that. And then from there, we could have multiple options, right? Because if two senders both go to the same node, and then seems like I don't know. All right, so then we have to choose, and it doesn't matter which. It does matter which one goes where because they're going to different destinations. Why is counting so hard? I'm bad at counting. Okay, yeah, I don't know what else to do. Let's see. Something we can cheese. Let's see. Maybe K is 0 is very meme or something, and I can just write it out really quick. I feel like, wait, no, because there's no, whichever direction you go down, you're not actually guaranteed to get to where you go. No, you're not guaranteed to get where you go. Wait, I feel like it'll be something like the number of like like the in degrees. It'll be some sort of in degree formula. Maybe if we take an in degree, because like for every in degree, because I have like 3 different. That represents a new option, right? So I have 2 options. Nah, but that doesn't necessarily, yeah, because you have in some in degree, which doesn't actually carry any option at all. So I'm gonna cut out. Okay, so then what if we? Okay, so what if we do like a quick Floyd workshop? We get all the from here. This node is reachable. Wait, so by taking a path to some node, you're not actually. Are you? Wait. You're not blocking anybody, but you're also removing some of their options. It's actually a bit like floats, right? Because you have a bunch of sinks and a bunch of sources. Oh, okay, it's not really like flows. It has some kind of similar thinking, I think. I don't know. I don't really know flows. Yeah, okay, so k to 0 is not that easy. I assume k is 1 and k is 2 will be harder than that. In 10 minutes. As soon as recording's still going, it might have died. Things are refusing to be stabbed. Come on. Why is this so difficult? When you can AK gold, but you can't frickin' spear some vegetables. Okay.
Good enough.
Okay, right. These are all my best submissions. Yes. Okay.
I feel like it is maybe something like that. The Floyd Warshall, you see. The problem is you don't know. I don't know how I would. Because, like, if one node takes one path, it could block off a different one. Like, not completely, it would just remove an option. Actually, although, let's subtract 1. Is there an easy way to calculate, like, ways from this node to this node? I think there is, right? That's a pretty simple DP, isn't it? And then, okay, I have 5 minutes, so I'm not going to be able to implement anything, but, right, so you count ways from this node to this other node, right? And then, I guess you could choose a node to... Now my disk is almost full and my computer's yelling at me. The recording's almost certainly been forcefully shut off at this point. The recording symbol's still going, though, so I'm not sure. Okay, so then... Right, okay, then now you could choose to move... and then, okay, so you can figure out how many different ways you can move. No, it still answers the same recursive problem, because then you need, because, like, depending on which one you chose, it might, that affects things differently. Yeah, I don't know. Yeah, this point, basically just waiting for the time to run out. Even if I get some genius idea, I'm not going to have time to implement it. $250 left. Incredible.
Maybe I should delete some stuff to prevent my computer from molding and exploding and killing this recording. Let's see. I don't think I've uploaded any of these. Yeah, so I can't delete them. That's sad. I should have figured this out beforehand. Alright, but yeah, I mean, it's not much to see here anyways. At this point, I'm just, like, waiting for time to run out. About a half gig of memory has been eaten up since I last checked how much memory there was. Okay, I deleted some random Windows ISO thing because I have another copy of it. I don't even know where that came from. I think I was thinking CTF thing. Maybe they did Windows. Okay, so if my recording is still alive, it should stay alive for the next couple minutes at least. But if it's dead, it'll probably just be dead. Okay, 2 minutes. Yeah, I don't want to submit anything just because if it's wrong, then I lose what I have right now. So. Yeah, so my little score would be. So I got 1 plus 5 over 24 plus 4 over 3, 469. I'll take that. First time in flat. Okay, finish the orange juice. 50 seconds remaining. Okay, let's see. I think this went, yeah, I think this went pretty well. The fact that I solved the problem means it went well. The other two, that was basically what I was looking for, right? Solve the first two subtasks. Solve the first subtask with 2 problems. Then I solved the first subtask with 2 problems. It's just that with the problem, I solved the whole thing. So that was pretty nice. Okay. Yeah, but I'd expect, I think I said this already, but like, I feel like these problems are something that like the top people probably like solve all of them. It's a little weird since I think the Open's supposed to be harder. But I'm pretty sure the Gold Open was also easier than the other contests this season. So I don't know. At least it was easier based on my experience. So I don't know. Maybe everyone else found them like super hard or something. Okay, and time's up. Yay. Okay. Yeah, that's it. That is the end of USACO for this season. Funny to think that at the beginning of the season I was like, I'm going to make camp this year. And then gold happened. It's just like, no. So that was sad. But I mean plat now, so it's an ego boost at the very least. Yeah. And I guess I keep doing like code forces and stuff. I should probably actually practice for plat. And not just pray that everything is bashable with lazy seg. Okay, yeah. So I'll probably go do that. Yeah, if the recording hasn't died, I'll stop it now.